As you can see, we're in a bedroom and we have a e-scooter here that contains a lithium-ion battery. What this really is an experiment that we're setting up where we're going to look at the impact of that battery if it went into thermal runaway. We want to understand what that impact would be to any occupants that would be in the space, and of course how the fire would spread within the space. In preparation for this series of experiments, we've looked at, with fire departments, fires that they have actually had in buildings where they see the e-scooters in place being charged overnight and blocking egress, or being in someone's small rooms, they charge it in their bedroom overnight. Not a good thing to do. So based on those fires, those actual fires, we've set up this scenario where we have an e-bike in a 12-foot by 12-foot bedroom. And in addition to that, we have a significant amount of instrumentation so we can understand how the thermal environment's going to change, what kind of chemistry smoke will have, and how that would impact any people that would be stuck in this spot. In this scenario, we have an e-scooter that would be located near the front door, the exit door, and would be charging. Again, this is an example drawn from actual fires where occupants brought a e-scooter such as this into their home, put it in front of the front door to charge it overnight, and when it burst into flames, people in the apartment or the home were unable to escape. When they get into a thermal runaway situation due to overcharging or perhaps a damaged battery, they can hit a peak heat release rate of 1.5 megawatts. And for a typical residential scale room with adequate ventilation, you only need about 2 megawatts of energy to flash that room over. We want to try to understand the timing of that. How long does this take? Are there any precursors, any warnings? We have our structure instrumented with smoke alarms, just as people would have in their homes, in addition to thermocouples, heat flux gauges, and pressure transducers. One of the essential measurements we make in a fire experiment is measuring for temperature. And to do that, we use thermocouples. Here you see we have a thermocouple array, so we can look at the temperature gradient as the smoke starts to layer at the ceiling and build up and work its way down. We have some gauges here that measure both total heat flux and just radiant flux. Next to that, you see our sampling ports where we're measuring oxygen, carbon monoxide, and CO2 concentrations as the air becomes involved in the combustion process and we generate smoke that contain those products. We have some other ports sticking out of the wall. Those are to measure pressure. We want to get an understanding of just how much pressure is being built by a rapidly developing fire from a lithium-ion battery. We also want to gain video records of the experiment. So we have cameras located up high in the space, as well as down low in the space where we have a thermal imaging camera protected behind the wall. We're using the thermal imaging camera to see if a firefighter were entering the room or entering the space, what they might see if a bike was going into thermal runaway, or potentially after suppression, if it was still hot and had the opportunity to potentially go into thermal runaway. What we want to see here is basically what kind of hazard does the bike itself present. And once we see that it has gotten back to sort of a steady state burn, we're going to have the firefighters come in and put it out right away. After the fires, we're going to come in and we're going to measure the water runoff and understand what the chemistry is in the water that was used for suppression and is running off the fire scene. And we're also going to measure the air that remains in the fire scene to see what fire investigators and firefighters doing mop-up might be exposed to. Depending on how the battery case is built, in some instances, the battery case may burn away or be damaged. So when the fire department arrives, they can easily get water on all the cells and cool them down and get them below their thermal runaway temperature. There are other scenarios where the batteries might be encased in a material or in an enclosure that the fire service has difficulty getting water directly on it to provide that cooling. So again, they may knock the fire down and cool some of the batteries, but there may be other batteries that are encapsulated or enclosed in insulation and they're heating, and the fire department may not realize it at that point in time. In terms of challenges for the fire service, lithium-ion battery fires produce a tremendous amount of smoke in many cases before they ignite. And much of the smoke is flammable, or it could reach a concentration where it's actually explosive. So there could be an explosion hazard. Other challenges, depending on how the battery case is composed, is that the firefighters may knock down the fire they see, and yet there could be some other batteries that are in that device that are on their way to thermal runaway. So as they attempt to move the battery out of the fire apartment, it could reignite and burst into flame again. Many fire departments are now calling the hazmat team to deal with them to help remove the material from the building in a safe manner and try to prevent reignition while it's in the building. What we learned from our first series of e-scooter experiments was that the fires grew very rapidly. Between the time that smoke was initially showing to the time of an explosion or a jet flame was typically on the order of 15 to 20 seconds. So again, extremely rapid fire growth, which then led to a rapid transition to flashover. So if people were in the room of origin, those rooms of origin became untenable, certainly in less than a minute, if not sooner. Folks that were remote from the area of origin, if the e-scooter was blocking their egress, they would lose that egress path again very, very rapidly into the fire. There's really not much time to react, so prevention is one of the key points in terms of battery usage, lithium-ion battery charging in your home. Recommendations: we all have lithium-ion battery devices in our home. Charge them while you're awake, especially larger batteries like e-scooters or micro-mobility devices. Don't charge them while you're sleeping. Don't block your means of egress while you're charging that device. And make sure that you use the manufacturer's approved charger with the appropriate battery. And last but not least, if you have a feeling for some reason that the battery may be damaged, please don't put it on the charger. For more information about our research with lithium-ion batteries and e-scooters, please go to our website, fsri.org, and check on our progress in terms of videos and reports that we've made.